Hello, welcome to this video on the spinning barrel or the PLeane gun. I'm making this video in response to a concept of my flat earth friend who believes that the earth is not spinning. So I challenged him on this argument, and what is your main premise? And he believes if the earth was spinning, the moon should be spinning counterclockwise. But the moon is not spinning counterclockwise. The moon is locked in a tidal lock where one face of the moon faces the earth for 28 days of its cycle. So I responded back with, okay, look, there's well documented evidence from the Coriolis Effect that the Coriolis Effect being that wind currents and projectiles travel accordingly, they spin, they drift according to the Earth's rotation. And he responded back with, well, I believe all this videos on projectiles and guns shooting and long-range artillery is more attributed to the Magnus effect and spin drift rather than the Coriolis effect. And I thought, okay, right, have an open mind. So where he's up to is, if I just get the globe out, which I know you flat earthers love this when I bring it out, so I'm ready for some big comments on this one. So here, just get the globe out and I'll just show you what Coriolis effect means. Basically, quickly, the Coriolis effect is the phenomenon because the equator is larger than the poles, the surface velocity is travelling faster. So here, if I was to fire a projectile here at Tasmania to Cape York, if it was a long-range projectile, I would fire here, and because it has this distance here is travelling faster than this distance, the projectile would travel to the left. Now that would be very noticeable on a long-range artillery shot from Tasmania to Cape York, but most artillery and long-range rifle shots are usually nowhere near that distance. 10 kilometres is the distance we measure. So what we needed was a very accurate gyroscope. If we could fire short distance, 10 metres, is it possible to measure the Coriolis effect over 10 metres? So that's where I thought perhaps the spinning barrel may come into it, because that's in fact what I invented this for. Okay, and just to elaborate that concept where he's talking about the moon and the spinning, when the Earth and the moon evolved, the evolutionary forces settled down. The moon was spinning at a great rate out here somewhere, and the Earth was spinning probably faster than it is now. But all of a sudden, during our present lifetime, the moon and the Earth became what was called tidal lock. So the moon goes around the Earth, facing the Earth, with the light side and the dark side away, and takes 28 days to go around the Earth. Now, what he's saying is the gravitational flux from the Earth spinning should make the moon twitch, at least twitch, or flip around in a counterclockwise direction. And I thought about what he's saying, and actually making sense. So I'll just explain that a little bit better on the whiteboard. So what he's saying is the Earth spinning clockwise in this direction, the moon should spin counterclockwise. Oops, my dyslexia again. It should be counterclockwise. So how does that happen? Well, between the Earth and the moon there is like he said, a gravitational flux which acts like a coupling. So if this thing is spinning, this thing here should spin as well, but they don't. So I can't explain why they don't either. And everything I read or about the centre of mass and between the two, moon and the Earth, don't make sense, because I can't see anything that can override this huge magnetic gravitational flux. Perhaps there is some magnetic flux as well, I don't know. But there's certainly a huge gravitational flux between the two objects, which I would say they would spin like a fluid drive in an automatic transmission. Alright, so possibly the best way to explain this optical trajectory is when we sight a gun barrel, we usually do our first shot. We basically sight the target through the barrel. So line up the barrel. This is very hard to do. And we look at the target and we do our first shot and the bullet hits somewhere. So from then on we adjust our sights to this position because that's where the projectile hit. So that's where from now on we put our sights. But during this transition, this was the true path. This was the optical trajectory. Now here is the projectile's trajectory. Now over short range, less than 1,000 metres, it really doesn't make much difference. These two things are so close it doesn't matter. But when measuring the Coriolis effect for long range artillery, it does matter. So to put it in simple terms, if I want to shoot a rabbit 5 kilometres away, that's its optical trajectory where I'm looking at. But to shoot it, I fire down here somewhere, and somehow the bullet hits the rabbit. So over long distances, which is what the Coriolis effect is measuring, there's a discrepancy. So where are these people really shooting at? Where is the vector alignment to do all these measurements from? So that's the question my friend was saying, and I can see his point. There is no true vector alignment. The optical and the projectile trajectory are two different things. Okay, so why did I invent this spinning barrel? Well, I needed a very accurate gun. And why? I wanted to measure the neurotransmitters across the synaptic cleft. Now, what happens is, I believe that these neurotransmitters fire across this synaptic cleft and they actually spin. That's why we can jump up and down and these things don't drift. Now, I invented this gun as a part of to prove this theory, a part of my spinal cord research. And one of its main functions is to create the optical trajectory, which is what most gun owners and long-range artillery leave out. So the next video you'll see is just me demonstrating how the spinning barrel is made and the components, so I'll move on to that. So basic setup of the PLeane gun is this optical laser that travels down the bore and illuminates the target at the far end. The laser doesn't actually touch any part of the barrel, so it travels down the barrel without any reflection, giving us a pure dot at the far end without. So that's how we check the alignment. The barrel is, as we could see, as we know, it spins from a turbine, and the barrel is allowed to slide back and forth. It's under a spring loading, and this eliminates any standing waves and recoil on the barrel. So as we can see, it never once moved. The spin rate, as I said before, is roughly 1 kilohertz, and here's our optical detector and some contacts for the pickup for the hot wire that releases the spring. On the other side is the air delivery, so that our air delivery system is basically just a feed from our air compressor, and a tap to regulate the speed. So that's the basic setup. Of course, you may have seen that spring-loaded dampener, which is also the other contact which allows for dampening and contact. Okay, now the experiment's going to be rather involved, so we'll have to just give you an introduction to what's going to happen. Our experiment and our aim will be to define this optical and the projectile trajectory. Now that's very important and the main crutch of our experiment. Now how I'll tend to do that is a laser beam will travel down the spinning barrel all the way to the target, and what we'll do, we'll use the fact that when we look at a laser beam, there's lots of little speckles. It's made up of lots of little speckles, and to get the true optical alignment, we'll use a pinhole camera which will actually focus in on one or two of these little speckles, and if any of them move, we'll know that we're out of alignment. So you'll see me do that with some in the experiment. Quickly, how the spinning barrel works, it's very simple. There is a small brass projectile in a small brass barrel. The projectile is 4 millimeters by 8 millimeters, and what happens is there's a small fuse wire here at the end of a spring and a heavy spring, which I can vary the spring. I can get possibly 10 meters, and hopefully I'm aiming for a travel time of 2 seconds in 10 meters. So a very long shot, but very accurate. So this wire melts with an electrical contact, releases a spring, an anvil hits the projectile and shoots it out. So that's basically the operation of the spinning barrel. There is no air compression, there is no explosion or it's just purely on a spring pressure. The next objective will be, can the spinning barrel stabilise the projectile? Now this will be to prove how stable and how accurate this gun is. So what we'll just use a standard wad cutter, which is virtually a projectile with a hollow nose on it. But to prove that we can stabilise this projectile, what we'll do is I'll make a buzzsaw bullet out of it. So what we'll do is we'll actually remove one of the front faces, and these are these bullets that tumble head over tail, and you hear that characteristic buzz noise like from a ricochet. And therefore we should end up somewhere at the end of the experiment proving that this spinning barrel can actually produce a micro or miniature gyroscope. So here we go, back out in the experiment. Right, here we are at the spinning barrel assembly. We're using a laser level to give us our level references. So the laser beam coming from the laser level down along the floor, across to the spinning barrel assembly. Just notice the laser tip on that brass tip of the barrel. Swinging around our 4 metre mark from our ruler, you might notice that faint pink line of the laser light travelling along, coming to our target, and there's our compass bearing, and we're just approaching the target itself. What I'll do now is I'll just steady the camera, and I'll look for the focus on that mirror for our bore scope. So here we are, steadied the camera, zooming in on our target, which is this mirror at the moment, and I'll activate the bore sight now. I might just kill this light. Okay, there's our vertical reference. I'm activating the laser bore sight, looking for any hologramming. hard to see. Might kill another light. Right, that looks pretty good. I'll just spin the barrel. Oh, that looks very good. Okay, look, I couldn't see it from back there. I'll spin it again. Okay, I might put a bit more speed on. I'll just put the compressor on the turbine, but that to me looks like a perfect circle. Just activating the out here at the compressor. Okay, not spinning it that fast. Alright, I think we have a perfect, there is no hologramming, so we're actually looking at the true optical centre of that spinning barrel. I'll have to look at this on the camera later on, but yes, that's perfect. Okay, now we'll just set up the shadow mask to make sure we've got the other systems in line. Right, I just placed the shadow mask in front of that target, and I'm putting it on the 900mm point and just tweaking that. There's our vertical line, our vertical datum, and our laser dot are in line. Okay, spinning the barrel one more time. Okay, well I think we have a perfect, yeah, right, now, because I haven't any light splitting and this is a poor man's setup, we have to make a pinhole camera to give us our reference. Be nice to have a light splitting here, but hopefully this will work. Okay, we should see the dot appear on that. Right, I think we've got it. Okay, look, I'll go back over to the... Yes, I'll go back over to the target. Now we should have our pinhole lens, and we have a datum, horizontal datum, a vertical datum. Well, I think we've got everything perfect. Oh, focus you. Oh, I'll leave some light. Just bear with me, guys. This is so important. This is everything here. This is. So we have to get this dead right. It's so important. Okay, got focus. I'll kill some lights. All right. Yes, we've got our light back again. We're going to have a laser from our pinhole. Geez, that's finicky. Why is that so finicky? Stand by one more time, bear with me. Okay. Right. Yep. That's perfect. The only way to test it now is to take the barrel up a bit faster. I might put the other camera on that so we can actually see that. So stand by. Right. Yeah, that looks square to me. I've just put the camera a little bit more square to the mirror, and we'll go over to the right. I'll just activate the the air. Let's see what happens. Okay, that was 300. That got to about 310 Hertz with zero hologramming. Right, I think we've got we are looking at the optical pathway of that spinning barrel. Okay, here we go with the static firing. This won't be pretty. I'm expecting a big keyhole. Okay, here we go with the static firing. This won't be pretty. I'm expecting a big keyhole. Okay, that doesn't look pretty. Focusing on the... Yep, shadow mask. Shadow mask looks bad. And the target looks bad. Right, okay, that was obviously no key. It was a horrible, messy shot. Okay, I just checked that the... I'll just kill the... we'll come back to the check with the laser, make sure nothing's moved. Shadow mask looks fine, nothing's moved. And the target looks fine. Coming in closer. This is the main one, of course. Okay, the dot hasn't moved. A bit closer shot of that ugly hole. Right, we'll move on now to spin at possibly 500 Hertz. Right, here we are at, I've set the counter for 200 Hertz rather than 500 Hertz, so here we go. I think I'll do it in small increments. Turning on the air. Okay, that counter went really wild. I hope everything was alright. Stand by. Right, here we are at, I've set the counter for 200 Hertz rather than 500 Hertz, so here we go. I think I'll do it in small increments. Turning on the air. Okay, that counter went really wild. I hope everything was alright. Stand by. Okay, it's coming in on the shadow mast. That dot looks a little bit rounder, which indicates to me that the projectile is becoming more stable, not less tumbling. Let's go to the target. Yes, that to me looks like the projectile is stabilising there's a nice bit of round cut. First signs of wad cutting. Okay, let's go and increase the speed. But we notice now that the trajectory has changed to the left. So we're going left of our vertical datum. So here we go at, with the counter set at 500 Hertz. Turning the compressor on. I've just parked some green stickers over top of those last holes, just in case you have a duplicate hole. Okay, that looks, let's go in here on the shadow mask. That to me looks almost like pretty close to a wad cutter. It's getting closer to the centre line, becoming more stable. Over to the target. Okay, here we are at the 700 Hertz test. I've removed that, I've gone to the standard projectile, the wad cutter, without the small nick in it. I think we confirmed that the spinning barrel actually does stabilise an unstable projectile. So what we'll do now is just start up the speed, and hopefully we should be getting closer to that vertical datum with a clean wad cutter. Stand by, here we go. Okay, so that's what I expect, straight through the centre of the other hole. Alright, very little difference between 500 and 700 Hertz. I'll just come closer. Right, this is probably, now we've reached our most important part. As you can see, we've gone straight through the centre of the 500 Hertz. That was with this unstable projectile as well. I would say now, although the turbine could go a bit faster, I don't want to push it today. I think things are starting to deteriorate. I should regroup. The counter is not acting according to what I expected, so there's a bit of things happening there. Alright, let's just remove these tabs and we'll see what's going on. Right. I believe this is the hole here with our latest 700 Hertz. So this hole here was the optical trajectory. This hole here at 700 Hertz is getting closer to the optical trajectory, but I don't believe, possibly if we go to say probably 2000 Hertz, I believe the Magnus effect will move the projectile to this point here. So it's hard to say. Alright, let's go to the target now. We'll see what happened there. Right, here we are at the target, and almost perfect wad cutter on that last shot, and I believe we'll just remove the tabs. It may have gone in the same hole as the 500 Hertz. Okay, no, a little bit to the right. Alright, look, the projectile is becoming more stable, there's no doubt about that. But this question of the optical trajectory and the physical projectile trajectory is still in question. Well, I think we definitely need more experimentation. This is the last one here, this hole here, and I'd say it's gone fairly deep. Yes, I can feel the end of the projectile, and it's gone in square. So it's gone into the polystyrene foam about 30 millimeters approximately, maybe a little bit more. There's a recoil bounce. Alright, I think that wraps it up. So, okay, let's return to the whiteboard now, and we'll do a summation. I was just summing up here. I just realised I haven't put the laser on to check if anything moved. Let's put some dates on here. March 2018, our bearing was 60 degrees northeast, our direction was east to west, and our maximum penetration we got was 30 millimeters. And there's the labelling of the targets. I'll just see what that laser turns out like. Hopefully nothing moved. Yeah, it looks like exactly the same spot, which isn't bad considering it's been jumping around like a screaming banshee. So my platform is pretty stable. Okay, thank you. So one last final static firing, here we go. Okay, so here's the result of that static shot. I'm thinking it keyholed on that tip there and elongated there. It's hard to say. Let's go to the target. So, fairly well bruised along that angle there, which indicates to me it flat shot on the side. But again, it's interestingly enough, it's because it wasn't tumbling at this buzzsawing it wasn't buzzsawing like the static shot up here. It's sort of tended to be here with the other group. weird. But look, here's some test results from previous tests. Mostly flat shots. One wad cutter, which is a random. Another group down here were flat shots. This is from different spring pressures, but indicating to me that it's totally unreliable. The most reliable comes when, of course, when the projectile is spinning axial. So that was an undistorted shot, undistorted projectile. Alright, now we'll just go over the summary of our results from our experiment and the end of the video. From our summary, from our shots in our experiment, we know that number one, our optical and projectile trajectory can be defined. Although I didn't get to my 800 Hertz, I can assure you that this barrel is tuned to hit the centre at 800 Hertz. Now what I'll do is I'll make up another video. I'll try and get this counter working, and I'll tag this on in a couple of days' time to show you that the 800 Hertz in fact is tuned for the optical trajectory of this barrel. But what we can find is, did the spinning barrel stabilise the projectile? Yes. We've seen up here our static shot was over the place. At 200 Hertz we really couldn't see much happening, but at 500 Hertz our unstable projectile started to become stable and started cutting something like a wad cutter. So at 700 Hertz I was cutting a pure wad cutter. But I was hitting here. So my projectile trajectory was to the left of the optical trajectory. Now, as I will later demonstrate, 800 Hertz will give me the optical trajectory and the projectile trajectory will hit at the same spot. But if I was to spin this barrel faster, or as in a different type of projectile, the optical and the, say for example I was to go to 2000 Hertz, I believe the projectile trajectory will actually land up here somewhere, just from this Magnus effect or spin drift, which was my friend was saying. So over a long distance, the distance between here and here and here and here is a huge amount. So where are these people aiming these guns to get this Coriolis effect from? You know, that's okay. So finally, yes, our spinning barrel can produce a gyro. So if we want to continue the experiment to put projectiles in a vacuum so we can isolate the air currents, let's do some more testing. So yes, we can go further with our experiment. And finally, look, I've still got a patent on this, so if someone wants, it may be beneficial to people who manufacture ammunition or barrels or something. Someone might even like to try something, a live fire with a longer distance shot, so that'd be interesting to see how that went. But I can't do live fire, so okay, well I think that's it. Thanks very much.